So I'll restart the video. Here we go. So these are some of the early lasers and some of the common ones that you'll see. So the very first laser in 1960 was the ruby laser, and it just had a strong enough absorption that you could get a population inversion with the ground state, which is pretty rare because you have to deplete the ground state. You have to get so many molecules or atoms, in this case chromium atoms, out of the ground state that you have a population inversion. A lot of times you have to get a population inversion with a level that's not the ground state. So look at the two systems on the right. Look where the laser is. The laser is not connected to the ground state. And compare that to the ruby laser. The ruby laser, the laser is connected to the ground state. So the ruby laser is pretty unique. You have to have a super strong absorbing medium. And there's not a lot of chromium in a ruby gem to produce that strong red color. Okay, so it's a strong absorber, and that's what helps in that situation. The middle one is the neodymium YAG laser, probably one of the most common lasers. Your green, some of your green laser pointers, and then our green laser that we have on our Raman spectrometer is a neodymium YAG laser. So that was 1964, so not much longer, not long after the ruby laser. And then the helium-neon laser. This is a really weird one. The helium absorbs the energy from the power supply, okay? And so it gets excited, and you can see it's the triplet and the singlet S states that are excited. So the 1s electron jumps up to the 2s, and there's two ways to do that, two J values, and then that bumps into a neon atom. And so this is really weird. The helium gets excited and gives its energy to the neon atom. And so we haven't seen this in our class yet at all, where you have an excited species and they bump into each other and the excitation goes from one species to the other. So the helium, when it bumps into the neon, is de-excited, and now the neon is excited. And you think, how can that be efficient? Well, I don't know, but it is, you know. And imagine it's pressure dependent too. You have to have the right amount of helium, the right amount of neon, and the gas tube. That's another downside of a helium-neon laser is it's gas medium inside. It's a gain medium that's a gas, whereas the ones on the left are solid crystals. Okay, so when we say solid state, those would be the two on the left. Gas laser would be the one on the right. But it works pretty well, and so then we have a 1.2 micron emission that can be can laze, and then we have a 632 nanometer light that can come out. And many times that's the red one that you see. So the helium-neon laser is red, but there's also an infrared beam as well. And it's a population inversion with this excited state. And then those excited states, through non-radiative relaxation, can get back down to the ground state. And so those are fast, they're depleted very quickly with internal conversion. Here's the spectrum of the helium-neon laser. Doesn't look very interesting, does it? But when a spectroscopist sees this, they go, yes, why? Why would I be excited about this spectrum of a helium-neon laser? Just one wavelength, but what can I do with that then? You think about all the other sources, hot objects, right? An incandescent light bulb, which is all we had, you know, Edison's light bulb, it's just a hot wire, and it gives off a rainbow. It gives off a black body curve, where you have all the wavelengths to some amount, and it's hard to do spectroscopy with those. Whereas this, I can do Raman spectroscopy with this. If I hit a molecule with this laser beam, some of those photons will be scattered off elastically, and so that would be the Rayleigh line, but there might be a Raman effect, and I might see a peak here, and a peak there, and a peak there, and a peak there, and those would be the Raman scattered lines. And because this laser is so narrow, I can see the vibrational scattered lines. If I had a really fat, you know, incandescent source, it'd be really hard to detect the Raman effect. I have to use filters, and filters work. I mean, I can have a really bright tungsten lamp, and I could put a filter on it and detect the scattered light from the Raman effect. But it'd be really difficult. The peaks would be very broad because my source is broad. If your source is broad, your scattering is going to be broad. I could even do, since this is in the visible region and I've got a lot of visible detectors that I could use, obviously I'm detecting light that's of shorter wavelength. If I have a hot gas, one that might be thermally excited, I might be able to do anti-Stokes Raman. And so if I wanted to do combustion research, say I have a jet engine and I want to know how efficient the fuel is burning, I could look at that fuel plume, really hot gases, send this laser through, and I'll see some anti-Stokes lines. And so since these lasers produce such what we call spectrally bright lines, or very narrow wavelength width, then they can be really used for spectroscopy, and have really revolutionized spectroscopy, because especially since the solid state ones, the diode lasers, are so great. I mean, they're battery powered now. You can do spectroscopy with them. So here's your laser selection guide. This was a few years old, but you see we've got wavelengths of light that go. Here's the UV, the visible, the near infrared. I'll do NIR. But we're really, this mid infrared is a sort of a desert, if you will. And so if you were able to make mid-infrared lasers, you'd have a market. Now, why the mid-infrared is important? Because that, if you were to do direct absorption and you had a tunable laser, then you could do very sensitive vibrational spectroscopy, because the mid-infrared is that fingerprint region that we dealt with. We did the chlorobenzene, benzene. I mean, we could tell the difference between a ton of different molecules in the mid-infrared. And if we had tunable lasers in those regions, we could be very sensitive in terms of our spectroscopy in that region. This is a pretty neat laser. It's called an Exciplex or an Eximer. So whenever you go in for LASIK surgery or any other kinds of surgery where they're trying to destroy tissue or break things apart, they need very powerful lasers. They need a lot of light coming out of those. And these are some of the most powerful, they're chemical lasers, some of the most powerful lasers that we have. What's interesting about this is that only the excited state is bound and the ground state dissociates. So by definition, you have a population inversion. So every dimer or every excited complex is by definition in the excited state, and it can emit to a ground state that is emptied as this dimer or excited complex dissociates. So here's the energy level diagram for that on the left. So you might have AB star, which forms an excited complex, and then when it emits that photon, it hits a dissociative state and AB fall apart. So there never can be any ground state that's stable. Now, how might we make this up? If you think about the MO diagram, you could take an electron that was formerly in an antibonding orbital and move it up to a non-bonding orbital. And so you've increased the bond order for that excited complex. And so that's what we've shown here for the argon-fluorine Eximer laser. So you've got this electron is up on a 3s orbital on the fluorine. So it's non-bonding. It's on the fluorine. And then the remaining orbitals, you have a bond order that's strong enough to hold that complex together. When that emits, that electron goes down into this sigma star, and you end up with a bond order of about a half, but it has enough energy to dissociate. And so you have no molecules in the ground state. So this is a chemical laser. It's not very convenient in size-wise, and so, but it produces an enormous amount of power. And so when we were trying to decide as a nation what made the most sense for the most powerful laser to knock missiles out of the sky, this is the chemical laser system that we chose to put on this 747 airplane. So that's a 747, and it has got this turret on the front that is laser optics that can aim this laser and burn missiles out of the sky. So it's part of our Missile Defense Agency, MDA, And you can see videos online of that thing burning missiles, and I think I've got one linked here. Then they put one on a C-130, so that's what you see there. And it's, you know, little artist rendition shows the laser going down and hitting something. You wouldn't actually see the flash like that because it's pinpoint. And this video shows the C-130 system burning a hole in the hood of a car. Okay. So if you think about what's happening there, this plane is pretty far away and it's hitting a 1 foot by 1 foot target and holding the energy there constantly, okay? And there's no explosion. It's not like a grenade or anything like that. It's putting that energy really, I mean, they aimed at that 1 foot by 1 foot by square target, but they're really hitting a spot really small. So, you know, you can put that on, you can aim that on a missile, you could aim that on artillery shell, if you have the software right, and you can track those objects. So that's directed energy. We use directed energy in a lot of hobby shops, and some people have these in their garage for the laser cutters. And so they have CO2 laser. The reason they use a gas laser is pretty cheap. CO2 is dirt cheap. And you can make a pretty high-powered laser for that. And so those use CO2 lasers. They're very dangerous pieces of equipment because you can blind yourself so fast with one of those. So if you have one, be careful.